Very happy today to have Professor Harlan Spence from University of New Hampshire. And so Harlan is a professor at the University of New Hampshire Department of Physics. He's also the director of the Institute for the Study of Earth, Oceans, and Space at UNH, quite similar to NCAR, do everything. And Harlan received his PhD in geophysics and space physics at UCLA. After working on a NASA Polar mission at Aerospace Corporation, he then joined the astronomy faculty at Boston University, which is kind of going a full circle. Boston is where you get your undergraduate bachelor degree. And there he stayed for 15 years and became the full professor and department chair. And in 2010, he joined UNH. And Harlan's research interests include theoretical and experimental space plasma physics, cosmic rays and radiation belt processes, hemispheric, planetary magnetospheric, lunar, and aurora physics. He's the PI of the ECT instrument on Van Allen probe, the PI on 2 NSF CubeSat, and also the PI of the NSF FASD, the frontier in Earth system dynamics, studying center connection. He's going to give us some of the, every bit, sample every bit of that. Thanks.
Good, thank you, Hanley. It's my delight to be here, so thank you all for braving the weather, which I did not bring with me. It was 60 degrees when I left New Hampshire, so this was not my doing. We can blame the polar vortex. I'll show a different polar vortex here in a minute. So yeah, as Hanley mentioned, I am going to attempt the impossible, which is to talk about 3 different projects in one talk. And so it's either going to be a disaster or a joy, and I'll gauge that by your by your demeanor by the end of the top of the hour. So the different projects that I'm involved with really have a common thread, I would say, or several common threads. One is energetic particles. That's one of the, I'd say, the elements of my research program has been developing instrumentation to study energetic particles, but not just for the sake of studying energetic particles, but really to understand their impact. And so in this talk, I'm going to have a sequence of topics that really make the connection between energetic particles and the upper atmosphere. And so that, coming to NCAR, that just seems like the obvious thing to do. So the title of the talk is long and busy. The interesting asymmetry you see there is the name of this Frontiers of Earth System Dynamics, or FESD program at NSF. Is called Sun to Ice, but the title of the talk is Sun to Atmosphere. And that's kind of a hint that in terms of where this project has led us, we had hopes that we could be able to find proxies for interesting solar events in the ice core record, but that is leading us in a different direction now. So let me dive in, but before doing that, I really need to thank the extended teams that I'm fortunate to have with me, and I'll run through those when I get to it on the Sun to Ice project. The Firebird missions, Firebird 1 and 2, I'll talk a little bit about that, and that's an NSF CubeSat series of projects, and then the NASA Van Allen probes. I'd like to especially, though, call out Kathy Duderstadt, Chalin Wong, and Alex Boyd, who have really contributed a lot to the topics today. So originally, when we proposed Sun to Ice, our original goal is in the upper right-hand corner. At that time, it was believed, at least by many, certainly not all, but many, that chemical signatures seen in the ice core record, in particular nitrate enhancements, impulsive spikes in that chemical signature, seem to hold the promise for a connection to large solar events. And if we could then study these ice cores with the right time resolution, back into deep history, we could somehow look at what the sun was doing back into the 10,000, even 100,000 year range in a way that we'd never been able to do before, to really see what the sun is able to throw our way. So this was a pretty exciting topic with holding a lot of promise, but as I'll explain to you, we've now refocused that, and really what we've been able to show is that along with others who have been doing work in parallel, that we're unable to demonstrate this process leaving enough nitrate in the atmosphere, let alone getting that nitrate down to the surface into the ice to certainly account for the spikes that are seen, and most certainly not being able to use it to calibrate past events. So while we started in one direction, we've more or less put that to rest, but not quite, because the textbooks already have this sort of now what's becoming folklore of how we can use nitrates to see what the sun is doing. So we're now battling a little bit of the history as we move forward, but that's just the way science works. So let me give you a little background on how we got to that point. So back in the early 90s, late 80s, some work by the glaciochemists at Kansas University, Gisela Dreshoff and Zeller, they published a paper in Solar Physics in which they were looking at the GISP ice core record and identified an interesting period in what the chronology said was around 1859 of this large nitrate spike. You can see an annual variation in the nitrate signature here in the ice core record. And they made the association of that spike of nitrates with the now famous Carrington white light flare event that he observed. At the time, that spike seen in the nitrate signature from the GISP core record was the largest seen, and it correlated with one of the largest solar events in at least modern history, recorded history. So there was a reasonable, I think, at least idea that they might be related. Following that, others, including notably Ken McCracken, made the connection just between what might be a causal relationship. He tried to identify a physical relationship whereby the solar launches a shock wave that accelerates through various mechanisms both close to the sun and along the route, particles to protons in particular to very high energy, which then can penetrate low into the atmosphere and participate in ozone chemistry that produces NOI. Somehow, and this is where the magic starts to happen, you need to get rapid downward transport where wet deposition can start to occur, and it snows out and is entrained in the polar ice. So that was the reported mechanism. This continued to sort of take ground in the early 2000s. Palmer and the group, in that group, published a paper looking at statistical analysis of the frequency of these NOI increases found in ice core, now from Law Dome. So this is a southern South Pole. What they did is they looked at the average annual nitrate cycle compared with the occurrence of solar particle events. So they weren't looking at individual events, but they were looking at the cumulative effect over a year to see whether there could be an imprint of that in the nitrate variability, annual variability. And indeed, they found a statistically significant association. When solar proton events were more prevalent in a particular year, you tended to see a larger nitrate signal in that. So again, additional evidence for some kind of causal relationship between solar protons and these spikes that are seen in the ice. Well, that was one corner of the world, and scientists don't always communicate well across fields. And there was a whole other set of discussions going on, published in other journals and so forth, in the glaciochemist realm, who had long just understood that these nitrate spikes are noise. There are many things that can cause them. Why are those space scientists getting all excited about this? Of course, we know all these reasons why one cannot actually do this. So Eric Wolf in 2008 got, I don't know, so upset at us, basically, our community. I'll take the blame because I was one of the co-authors on these papers, so I'll personally take that, that hit. And so he went back and looked at some of the measurements that he'd been making in the more modern era. So take a look at the modern era when we have good space measurements and so forth. And basically in this one paper in 2008, again, it's a that space scientists wouldn't typically read. So again, the communities were busy at work on this, but not necessarily so well cross-strapped. And basically concluded that there was no clear evidence for a causal relationship, and furthermore, there really are theoretical arguments about why this mechanism really doesn't work. And a big that is the amount of nitrates that are produced and the downward transport, let alone photolysis. You turn the sun on, the nitrates migrate. There are a lot of challenging aspects. So around that time, Larry Kepko and I, when we were at Boston University, had a target of opportunity where we got a core that was being done at Summit, Greenland, a pretty shallow core, so not going back too deep into history. And at that time, we developed, or we implemented a new kind of analysis technique called continuous flow analysis that allowed us to do very high time resolution, about once per month type sampling. Well, no, sorry, about 40 times as good as that, almost better than daily resolution as opposed to the roughly monthly resolution of the prior ones. And so we published this paper in JASTP where we saw spikes seen in multiple core samples at the same depth and well resolved in time depth across those samples. And we had evidence for concurrent spikes seen in Antarctic ice cores, so we had both north and south. This was published in 2009. It's a very busy slide. Windless bite, South Pole measurements here, nitrates. These spikes are shown here. This is from the Summit core, and you can see these various spikes riding on a fairly noisy background here. Each one of these little black marks here is an indicator of a fairly large, significant solar event, either ground level events seen in neutron monitors or some kind of indication of flare activity. And the time here goes from the 1930s to the 1950s. So depth is this way, time runs this way with the inverse relationship between depth and time. So, you know, a lot of this is very circumstantial. And if we had picked maybe other big events, maybe the relationship might have been more or less compelling. At that point, we were still in the kind of groping phase to see what would go on. So the ice core community really did point out that there are many ways to get nitrate spikes in ice. And just within the tropospheric sources, you can have a biomass burning event, large forest fires in Siberia, the wind blows, dumps, and produces a spike in the ice. In the modern era, same thing with pollution. Events, smokestack vents in the tailpipe of the U.S. In New Hampshire, kind of the tailpipe of the U.S. Everything, all the junk flows east and then out over the ocean, and then dust from volcanoes can also produce things. Those are the primary sources, and then there are post-depositional processing. You have wind, photolysis, and migration within snow, let alone the inherent uncertainties in the dating. And if we're trying to associate with a known solar event, and there are solar events, which ones do you associate with? So number of sources. So Eric Wolf came along after the Kepko paper. It was kind of like point counterpoint. And in 2012, looked specifically at the Carrington event and pointed out that it was not observed in most of the ice core nitrate records. So it was seen in that one GISP one, but that was pretty much it. So one of the things that Wolf had been really pointing out is that looking at nitrates is a myopic way to go about it. And he was keen on being able to separate out the different sources by looking at different chemical tracers. So if you look at ammonium or sulfates, you can start separating out dust from pollution, from biomass burning. So I think the take-home message from Wolf's paper is here. We conclude that an event as large as the Carrington event did not leave an observable widespread imprint in polar ice. And certainly, he would have said this is a soft version of what he really believed, but the soft version reads nitrate spikes cannot be used to derive the statistics of solar energetic particle events. I think if you got him one-on-one, he was far less gentle than that in private, but that's what he was willing to put in print. So at this very workshop here in this very room, probably standing at this very spot, Don Smart and Peg Shea had an opportunity to confront this topic and contested that there would be dating issues and that maybe there was wiggle room and such. So at that point, things were really still very contested. And what we tried to do was put together a project that aimed to provide closure, and that's the Sun to Ice project. That started in late 2011. And as part of this program that's no longer provided for by the NSF called Frontiers in Earth Systems Dynamics. And in that, we had a program that is, and we still do, it's a 5-year project, we're in, just started year 4. We identified areas of controversy in this complex link of energy flow from the sun to the earth, ultimately to the atmosphere, and ultimately to some extent, hopefully, to the ice. That didn't work out so well. But we focused on elements within the community where the processes were contested or unknown. So we were focusing on CME initiation, coronal mass ejection initiation, and the evolution of those coronal mass ejections as they propagate through the interplanetary medium. Coupled with that then is the role of those fields and shocks in terms of particle acceleration near the sun and through the interplanetary space, and their transport from the sun to the Earth. Then the transport and transfer function, really, of those particles through the Earth's magnetic environment, through its magnetosphere, ultimately into the upper atmosphere, and then finally the polar ice physics. So this really brought together a very large initiative that pulled together a team that had the solar piece in terms of the modeling, the interplanetary medium piece, and geospace coupling as well. So it's been, I think, a really nice opportunity to bring that community together along with the core community that had really been operating sort of separately. So we kind of really forced the issue to have everybody in the room together. So today I'm really going to focus just on these last two pieces. These parts of the chain are not very controversial. The details of how that CMA initiation is, and we've made a lot of progress there in the particle acceleration, same there. Transfer through the magnetosphere, we know that pretty well now. It's that last bit that's been the controversial part. So I'll talk next about the effects in the middle atmosphere, and then that link, ideally, to the ice below. So these are some of the players who've been participating in our project, and you can look through the list. We have the folks over here who are associated with various pieces of it. So we have kind of a solar part, interplanetary part, atmosphere, and then ice part. And just to highlight a few people, Stan and Mike were part of the proposing team, along with Dan Marsh and Cora Randall. I think a lot of folks here know. And in addition, we've had a really good opportunity to work with Mike Mills as well. So our goal was to do sort of like what Eric Wolf did. which is to focus on space-age events where we have really good measurements of the solar protons and we have really good measurements of what was deposited in the ice, not just with nitrates, but with full chemistry. And really, the opportunity we had was that Jack Dibb, who is part of our team, has been doing daily snow pit collections at Summit for years and years. So every day they go out and sample, and from that sample, they do the full chemical analysis, not just nitrates. So that was a huge opportunity, and that allows you to separate out other signatures that if you only had nitrates, you might conflate that and confuse that with biomass burning or big storms that dump sea salt onto the ice or dust pollution and so forth. So once we sift through that, the goal was to see, are there any remaining events that look like those other sources are not likely, and whether or not we can use the Wacom model to try to simulate that and see if you can actually close the loop, if you will, on that process. So that work was completed and summarized in a paper published this year by Kathy Duderstadt. And we looked at 2 years of surface snow measurements. Again, these were made at Greenland. And we did, beyond the nitrates, we again looked at these other chemical tracers. And to some extent, you know, you could say that if you were looking for a solar event, people looked at nitrates because the ice core community was measuring nitrates for other purposes. That was the lamppost that was available, so everyone kept looking under that lamppost. But if you were to ask, what would I look for in the ice core record that would be an indicator of a solar event, you wouldn't come up with nitrates as the first thing to do. And I'll kind of close this section with a few comments on that. So this was our attempt to broaden the number of light posts, if you will, to really shine light on what the likely source was. So this is a cartoon that sort of shows the schematic of how this really works. So first of all, you are looking at a favorable season. You want to be in polar night, where you have a good polar vortex established, and that allows for that air to be essentially isolated. It just circulates within the pole. And then within that vortex, the produce the chemical signatures that ultimately might make their way down to the ice can descend over the winter pole and produce a reservoir of NOY here, which then has the challenge of getting down to the surface through a number of different possible mechanisms. So the key to this is an input spectrum of solar energetic protons into the polar cap, which then ionizes and dissipates the N2 and O2, which leads to this sequence of ozone chemistry, leading eventually to this reservoir here, and the final step would be the production or the deposition into the Arctic ice. So we went through that 2-year period, and that's from August 2000 to August 2002. This is the variability of that nitrate signature, and you can see that there are variations here that can be quite large. And of all the ones that we looked at, all those spikes, the 4 listed here did not have an indicator in any of the other chemical signatures that they could have been some of these other sources. So these were our candidates for looking for possible solar proton events. And indeed, there were some events that occurred in reasonable proximity to these events. So the November 9th solar proton event could have potentially contributed to these 3 spikes here, and there were a number of solar proton events in this time frame that may have been associated with this October 22nd event. So we ran 4 different simulations that attempted to sort of tease that out. Could this really work? So I'm going to focus on one of them here. This is from the 9th of November, 2000. And what you're looking at here is the vortex average total odd nitrogen. And that's plotted here as a function of potential temperature, which for those who don't think in that way, which is me, here's altitude over here, if you like altitude instead. That shows the conditions when you have no solar proton events and when you have an enhancement. And just focus on this middle one. You have a solar proton event goes off. It produces this influx of additional NOY, which then descends diabatically within the polar vortex down from where it's created at relatively higher altitudes down to the 30 kilometer or so altitude, and with an excess amount of 10 ppBV. So what you're starting with is a relatively thick background pool here of 10 to 15 in the lower stratosphere, and so you're adding a thin layer of additional material here, 5 to 10, at 25 to 30 kilometers after the slow downward transport. But the key here is that that's as low as it gets. It does not get lower, and it's a relatively small enhancement relative to the background. It's not a factor of 4, let alone a factor of 10 increase. It's a relatively small increase. Here's another way of looking at it. This is now looking at the total NOY column density. Forget about what altitude it's at, just how much more did we make. And the blue curve here, and this is the concentration versus time after the November 9th event, so showing 4 months or so here. The red curve is the model run without the solar proton event input into it, and the blue is with the solar proton event. And so there's roughly maybe a few percent, up to 5% enhancement, and over the entire vortex is about 5% enhancement from the solar proton event. And if you look locally at where's that difference greatest, it's about 20%. And contrast that 5 to 20% with the 400 to 500% increases you would need if you were to attribute those enhancements to the nitrate spike seen in ice. So not even remotely close to what was needed. Yeah, so the question was, when does polar night end? It's probably before the end of this, maybe right at the end of this run, I think. And that's actually another big problem is just the season will tend to really kind of blow things up. So it has to happen, if it's going to happen, it has to happen pretty quickly. And it's more favorable if it happens at the beginning of the season than at the end of the season. So it does shorten the window that way. So that was one event, and that just didn't seem to get us there. So let's forget about that event, and let's just now play God. So let's take the largest solar proton event in the past 50 years, and that occurred in September and October of 1989. And we're just going to pretend that it happened during the most favorable stable polar vortex winter of 2004-2005. And if that weren't enough, we're going to take the spectrum that occurred, those solar protons, and we're going to turn it up by a factor of 10. So let's just slam the atmosphere now with the biggest one during the most favorable nighttime conditions in the polar vortex established, and then do it again by a factor of 10. And the largest event we've ever observed in 50 years gave us an increase now a little bit greater, about 10%. So instead of 5% for the November 2000 event, it's now 10%. And if we crank it up another factor of 10, we're up to 60 to 70%. Now, it's important that what I'm talking about here is the total column density, not what's reaching the surface, but what's available additionally new in the atmosphere. And again, it's still well short of what's needed of the 4 to 5 nitrate spike, assuming that the entire atmosphere dumped itself onto the ice cap. So we've got a number of unlikely scenarios and a problem in terms of the magnitude. This is just a similar set of plots as I showed before, looking at this historically large event, again, during this ideal winter. And you still can see here that with the observed spectrum, you really don't get much production down below 30 kilometers. And even with a times 10 and this multiple event type signature, the peak number is still maybe getting down to 20 kilometers or so. So not enough. Can't quite get there. This is now showing the time history of these sort of things. Each one of these, this is back to the November solar proton event potential temperature and altitude over here for the NOY and the cumulative column density, just two different ways of looking at it, the local as a function of altitude and here as a function of integrated depth into the atmosphere. And the point really is that from the onset through several weeks later, you simply don't get enough down to make a difference, and certainly not what would be observed even if it all came down. These plots are similar in form to the ones I just showed. Now for the October 89, this play God type event where we've cranked it up by a factor of 10 at 2 weeks and at 6 weeks. And again, the column density increase from the non-SPE to the what was observed in terms of the spectrum, and then 10 times what was observed still doesn't give you enough. At most, you're almost getting a factor of 2 in that extreme case. But again, that's not at the surface. That's still fairly high in the atmosphere. So one thing we've been looking at is whether you can essentially bypass the pool of NOI in the lower stratosphere and then just basically produce the nitrates deep in the atmosphere, deep in the troposphere. And so that means you need a really energetic spectrum for protons to penetrate that deep. This is a plot that just shows 13 of the largest events ever recorded, and just trying to construct from that sort of a worst case spectrum that gives you lots and lots of particles at the highest energies, which are the ones that get down very deep. And you can see that here we've created one that has much higher intensity than any has ever really been observed. And so we can take that one now and place that one in, and even with this worst case scenario, even by a factor of 10, just another way of looking at the issue here is we don't get factors of 400 to 500%. We're maybe getting 50% at the most. So at this point, the prospects are not looking good in terms of, well, I would say the prospects of using the WACA model has been fantastic because it's allowed us to go beyond just the what-if scenario to actually do quantitative studies. So that's been fantastic and absolutely, I would say, revolutionary for taking this science and taking it from this sort of very loose associations that may or may not be the case to one where we can actually say yes or no. And in this case, I'd say the no scenario, even with this almost Carrington-like event that occurred back in July 2012, it didn't hit the Earth, but we even played around with that to see if it had an effect, and the answer is no. It's just another unremarkable. So even a Carrington-like event that was observed isn't working out. And I could go on and on with all the experiments we've done. This is that worst case 1956 spectrum times 10, and even that just doesn't get us there. So one could start playing really crazy games like saying, well, what if the sun had a flare that was 100 or 1,000 or 1,000,000 times what we've ever seen? That's interesting, but it's maybe less compelling than other things to do. So at this point, we've sort of paused and we're taking our breath. But this is kind of what we've concluded on the solar proton precipitation nitrate problem. It is true that solar proton events significantly increase the reactive nitrogen and decrease ozone in the stratosphere following these large events. And the November 2000 was a great example. However, there's no convincing evidence that solar proton events are related to these impulsive nitrate spikes. that leaves open the question of those 4 that we found that didn't seem to have any other marker. Where did they come from? What was that? Was it noise in the measurement? We don't really know yet. For the most part, most of those spikes, though, the troposphere provides alternative sources to explain them. And so that's been, I think, a very, very important progress in convincing most of the space science community, I would say at this point, that one has to exercise great caution and a lot of skepticism. We still have some remaining questions. We are playing the game of how large would an SPA have to be to produce something in terms of producing an event at the Earth. And I think a real promise there is looking at G-type stars and looking at stellar flares. And it is to me, pretty alarming that G-type stars can produce super flares like our sun never has done. So it does raise interesting questions about how within the class of sun-like stars, how is it that some stars, and it may have to do with the stellar rotation, which is another indicator of probably magnetic energy potential. So that's one thing we're looking at. Another is just looking at longer-term variations. Coming back to that Palmer work, there are certainly indicators on the climate timescales, not in the weather timescales, like the Gleisberg cycle, millennial variations, that we might be able to tease out of the ice cores, these longer-term variations. And then finally, are there alternative galaxies? And this was kind of the light post analogy. We've looked under the nitrate light post, but cosmogenic radionuclides, carbon-14 and beryllium-10, are other ways to get at large energetic events that would have produced signatures in the Earth and in the geologic record that we can use to study solar variability. So we're kind of refocusing ourselves on these. And so our next steps, just to kind of run through those, is what would it take, both in terms of fluence and spectrum, to produce what we see? Would such an event be within the scope of potential solar storms? And even looking at sun-like stars, I think there's interesting topics there. And we're now using particle energy flux from this coupled system to actually look at the impacts on the atmosphere, not down to the ice, but actually look at the impacts to the ozone chemistry. And finally, looking at these other indicators. So everything I've talked about so far has been protons, solar protons. But there are other sources of precipitating particles into the atmosphere, including radiation belt electrons. So that now segues from the NSF project to a little bit of discussion of where we are with understanding the role of the radiation belts around Earth and their impacts on the atmosphere. So this is a cartoon to scale that shows the Earth here and shows the locations of the average positions, and the color coding here shows the relative intensity in some very schematic fashion of the radiation belts that circle the Earth, discovered by James Van Allen, with Explorer 1 back in the late 50s on the first scientific satellite from the US. And in that, you can see that there's an inner belt that resides relatively close to the planet. This belt is produced by cosmic rays that smash the upper atmosphere to liberate neutrons. The neutrons decay in the form of very energetic protons and then are trapped in that inner belt. The outer belt is comprised of electrons that can be relativistic or ultra-relativistic, typically with enough energy that they can penetrate spacecraft. So they pose a radiation risk for satellites that orbit through that region, including GPS satellites, at the outskirts, geosynchronous orbiting, and low Earth orbiting spacecraft typically try to duck below both belts and for the most part avoid this radiation region. And if you're going to higher altitude, you typically zoom through them fairly quickly, but it's really the medium Earth orbit and geosynchronous orbits that are most at risk. I like this figure because it shows that the belts really do extend all the way to the upper atmosphere, and in fact they touch the atmosphere. And so that's what I'm going to focus on next. Just to put this in context, the Van Allen probes mission, which in my heart and mind still is the RBSP mission because that's how we started the mission. The mission was renamed from radiation belt storm probes to the Van Allen probes in honor of Van Allen. The name of the instrument suite we put together has radiation belt storm probes embedded in the name, so I'm still kind of stuck on that. And we did that on purpose, and I'll show you in just a second why. Well, it's here. Energetic particle composition thermal plasma. So it's RBSP ECT. You have to sort of sing Aretha Franklin as you say the name. So when they changed the mission name, we didn't like that, so we adopted RBSP. All right, it has been in orbit since September 2012. It's two identical spacecraft that traverse through the radiation belts and essentially measure electric and magnetic fields across the entire spectrum from DC component to high frequency waves, and particles from essentially zero energy to infinite energy, if you want to think of it, and coming from all directions and with all composition. It's very comprehensive. I think that's kind of the point, and I could get into details, but I think that isn't so important. And really the idea is to understand to the point of predictability how the radiation belts, how these, in this case, electrons in the outer zone are changing so dramatically in time and position. This is an example from measurements made on the Polar spacecraft back in 1997 of a DST is here, time is here. This is several days worth, showing a very weak population of relativistic electrons between an L of low L, so low, close to the planet, further from the planet, roughly out to geostationary orbit here, showing the outer zone electrons being mostly absent, almost disappearing, and then like a knife edge, appearing in great quantities, several orders of magnitude. This is a logarithmic scale, and then variability thereafter in association with a magnetic index here, DST. Sometimes a storm will produce a radiation belt enhancement. Sometimes a storm will empty the radiation belt, and you can see that there's a variability in the intensity of the radiation belt that tracks the solar rotation. So it's clear that the sun is doing something as well, and it's probably the high-speed streams and the buffeting of the magnetosphere that through resonant drift interactions. So we've got all these various things going on. So how do we understand this very powerful and subtle tug of war between acceleration that's creating the belts, transport and loss, which is tending to move particles around and in some cases actually lose them rather dramatically. So I'll talk a little bit about that. So this is our constellation of satellites. These are the radiation belt satellites against a cartoon here of the belts, and with geostationary orbit just beyond and other satellites moving through this region, we're able to build a pretty comprehensive picture of that particle environment and track it in ways that we haven't before. So I show this one because from this view you can see the pole is here, the spacecraft are more or less in the equatorial plane. If I go back though to this picture, the place where they touch the atmosphere is near the poles. With this NASA mission, we proposed and were able to launch some CubeSats that are in a polar orbit, samples those particles as they rain down into the atmosphere, the electron. And so this is called the Firebird mission. It's the Focused Investigation of Relativistic Electron Bursts, intensity, range, and dynamics. Sorry, it's a very tortured acronym, but one of our co-investigators loved the Firebird, and so we had to please him by coming up with a tortured acronym. Two of them were launched in December 2013. Another two are ready, basically on the Delta II right now, out in Vandenberg Air Force Base, and the prime mission SMAP launch has been delayed a little bit, so we're looking at a January launch. We were looking at a December 15th launch. And you can see that once you build them once, they look prettier. As you do them again, the students get better. This was a student lead project. And we've really got some exciting and excellent results. I'm going to run through this. This shows some of our successes and so forth. And I'm not really going to run through this either, other than to say at low altitudes, as we sample the foot of the field line where the particles are raining down, we do it with exquisite time resolution and energy resolution like never before in this really interesting range at energies that are important to the atmosphere. A previous mission to do this was SAMPEX, but it was probably too high of energy. It missed a lot of the lower energy particles that make a big effect. And as you know, you really want to have particles out here at the equator. That's where RBSP is, as well as measurements deep into the atmosphere, where the loss cone is, where those particles are, as they're bouncing along a field line, encounter the atmosphere ultimately. I'd like to show this figure, which is a great occurrence where we had the two RBSP spacecraft out at the equator. We had the Firebird units going through low altitude and sampling essentially the same field line. So we had one of the Firebird units making the measurements as this one RBSP spacecraft was passing through that same flux turb during a period when things were very stable and quiet. And from that, we're able to compare the fluxes that we see basically trapped near the equator, and that's the red curve. We can measure close to the particles that are going to make it down to the atmosphere. That's the green curve here. And then when you're deep in that loss cone, those particles that are really moving very close to along the field line here at the equator, within 4 degrees of the field line direction, Firebird measures those down below. And you can see the spectral shape is nearly identical, but there's about 100-fold difference in the intensity. And the theories of this is pretty consistent. The problem is that the amount of particles that can get into that so-called loss cone, it's a knob where you can dial the knob theoretically from about a factor of 10 to maybe a factor of 1,000. So it's fairly unconstrained theoretically, so having this kind of measurement really helps to pin down what's actually getting into the loss cone. So let me go through what I call the bucket list here, and that will end the talk. So if you were trying to measure how much is actually hitting the atmosphere, you want to know how much is hitting to be able to really understand the impact. So I have a list of things that I call the bucket list, and I make the analogy because the bucket is like the reservoir in the radiation belt where the electrons reside. So you can have a situation where you turn on the faucet here, and that's like electrons coming in from the tail, magnetotail, that fills up the bucket. Substorms do that, and it takes a typical time scale for that is an hour. And so that's like the analogy would be the reservoir went up because you added more to the bucket. So that's the source term. We also have this unusual situation where you have water that's kind of invisible because it's not energetic enough. So this analogy is really bad. It's kind of like you've got hydrogen atoms and oxygen atoms, and you get them together in the right way. They're invisible until they become water, and they suddenly come in. And that's my water wizard here. I don't know, plumber, I guess. And so he's magically creating that water. And what that really is are particles that were not at high enough energy to be seen, but they're resonantly being excited by waves that generates a new supply of energetic particles. So that's a local source. You have a source from outside, you can have a source from inside. You can also have what's called drift loss to the magnetopause, and this is what Jan and Mary Hudson have studied quite elaborately, where you have a bucket, but and the bucket has a boundary, but at times when the magnetosphere compresses, that wall comes down, the water splashes out, the magnetopause expands, and so now you've emptied the bucket. The water has gone off into the solar wind. All right, not the water, the electrons. My analogy is I'm taking myself too seriously here. So you've got that going on too. Then finally, you have a bucket, and it's a really leaky bucket. And it turns out that, think of the atmosphere. At each of the feet of every field line, every flux tube, some particles are drizzling into the atmosphere. And that's on a very large range of timescales. It can be impulsive, like microbursts, where it's literally milliseconds, to diffusive timescales, which is hours or days. And that's like a drippy bucket where you have lots of little umbrellas. And to estimate the amount lost, you have to consider all of these. So one of the things we'd like to do is to simply have a ruler here where we measure how much is in the bucket. We find a time when the only thing going on is precipitation. There's no source, there's no local acceleration, there's no transport, no magnetopause loss. We can measure how much left the bucket. We know it went to the atmosphere. So that's the goal. And people have tried doing this in the past, and I'll just show quickly total radiation belt electron content estimates. Very tough to do from low altitude because you're measuring just that tiny little bit at the foot of the field line. So we've kind of been motivated by that study, but we're using now the radiation belt storm probe measurements out at the equator. And I see time is running short, so I'm not going to go through the equations here, but let me just sort of jump to the bottom line. I'll show a few equations. There'll be a test here in a moment, and then we integrate. So basically what we do is we just add up everything through the orbit. Every time we go through the radiation belt over the course of the re-sample rate, so on the order of a fraction of a day, we integrate over all energies, all pitch angles over this range just to add up the total number of electrons that would be precipitating, and you get to this figure. So here's a year's worth of what we call the total radiation belt electron content during 14, from January out to January of 14, showing the dramatic variability of that quantity. So these are 10 to the 29, 10 to the 30 electrons. That sounds pretty impressive, but when you actually add up all the mass of the radiation belt, it's about equivalent to a donut, or a bagel, if you like bagels instead of donuts. So not much mass, but incredibly energetic. So the mass, the energy per particle is tremendous. You can see the variability, natural variability, which is, during this period, remarkable. So what we focused in on is this period right here in March. We know there was magnetopause loss. We can look at the phase space density, and we know there was no local acceleration. Everything was favorable, so that everything you're seeing here was pretty much lost to the atmosphere. So we have a direct quantitative measure of how many particles went into the atmosphere. And from this, thanks to some conversation with Stan, we can make an estimate of the hemispheric power. And so from this period here, we basically integrate at all energies about 50 keV, and it's about 100 gigawatts of hemispheric power over that 2-week period in March. And in my understanding from talking to Stan, this is maybe 10 times greater than a typical kind of unremarkable substorm, and maybe a factor of 10 less than a very large geomagnetic storm. And I guess my point would be that interval is no different than any of these. We just were able to use that to quantify the power, but you can see that kind of level is nearly continuous. Radiation belts are continuously dumping these electrons into the upper atmosphere, and we're now working with Cora Randall to estimate the impact of that, those medium energy electrons, to the middle atmosphere. So I would say, just to bring that to a close and bring the talk to a close, we've really started to, I think, get a very good handle not only on the proton precipitation story, but also the electron precipitation, using this new quantity here that we've been able to quantify much better than before, just given our ability. We've also been able to, and I didn't talk about this at all, sort it out in terms of the energy. There's a seed population that gets accelerated to this core population, and from that we're learning quite a bit by that. And the time lags tell us a lot about the process and physics at work. So our next step really is to explore that variability with both the external and internal drivers, and also ultimately, and we're not quite there yet, is to estimate the impacts of that atmospheric precipitation loss during favorable interval. And I will say the electrons certainly don't get down to the surface. So with that, I will close and ask for any questions. And I've had to change the title. It's now Sun to Almost Ice. So thank you.
Harlan?
Very interesting, Harlan. Good talk. With regard to the last thing you were talking about, the total radiation belt electron content, have you compared the sort of plot that you have there with just what you would see at geosynchronous orbit to see if how that maybe explains or relates to what Jeff Reeves saw, where do you get a different picture than what he saw about the increase, decrease, or staying the same?
Yeah. Funny you should mention that. Yeah, let me just, I didn't know you were going to ask that, but I did have this plot, which shows the Reeves type plot and what you get when you look at the total radiation belt. So this is from geostationary orbit, and this is from integrating over. So there's a similar kind of shape, but we're just starting to dive into that now, but that's exactly the kind of thing we're going to be looking at. I'm glad I left that figure in.
So I'm just curious on the similarities and differences between the Firebird CubeSat and Shinlin's CubeSat. The radiation belt CubeSat seem to be one of the few that I've seen that are actually producing scientifically usable data. And so how similar are those two things in terms of like the core instrumentation? Are you guys using the same reptile kind of radiation detector, or is it different? Or
It's a good question, fair question. I would say that both the Colorado CubeSat and ours use fairly simple detection techniques. Theirs is way more sophisticated. It's borrowing from the same kind of instrument that flew on the RBSP mission in a miniature form, involving 8 detectors to make up measurements with really good energy resolution. Ours uses pretty dumb detectors made by the same company, but just configured in a different way to get really high time resolution with pretty good energy resolution. So we're very complementary. They have very low time resolution, but good energy. We're just kind of the flip of that. And we have two. We're really looking to separate spatial temporal. And that's why we wanted to have the high time resolution, so as the two traverse the same region. So I would say that a similar kind of science goal, but coming at it from kind of two different directions.
Can you go back to your slide where you were estimating the 100 gigawatt input?
Yeah.
I'm interested in the interval that you're.
Oh, the period?
Yeah, what you're integrating over. You say 100 gigawatts of hemispheric power over a 2-week period. Is that averaged over a 2-week
Yes.
period? Okay.
Yeah. Yeah. So it's probably a little bit higher at the beginning, and it kind of winds down toward the end.
Okay.
Yep. I mean, this is all in a sense a lower limit too, because there probably are additional sources. Even with a very flat radial gradient, we'll still have some radial diffusion inward from the outside, and that's very hard to estimate, and that would tend to be replenishing this as it's draining. So we may be underestimating actually the amount actually precipitated.
Harlan, I just wondering how you integrate those. Are you integrated over entire polar cap or integrated over auroral zone? Because that would probably make a difference.
Yeah, so the integration really is over the entire radiation belt, and we just assume that's filling up the entire hemisphere. And I haven't been very careful here. I would take these numbers. It's the last kind of slide I showed. I should have put a big question and draft on it. So I wouldn't trust this probably within, maybe even a factor of 2. But it's going to be limited. It's not going to go up above L of 6, so it's going to be subaurora down to mid-latitudes.
And also your reference about 10 times greater than the typical aurora power, it's not during storm time. During storm, even aurora power goes to 200, 300
Yeah,
gigawatts.
we'll be much bigger. Yeah, so it's probably in the middle of maybe the range.
Just a curiosity-driven question, Harlan. That was great. The mega G stars. What was the motivation again to look at those? Just, I'm very curious about these things.
So yeah, if you look at the occurrence frequency of flares, and I'm trying to remember the numbers now. I think the maximum you get out of the sun is something like 10 to the 30 ergs, if I recall something like that. And if you look at the statistics of super flares coming from the super G stars, and you look at enough of them, you get a distribution that's really a distribution as much over time as it is over type of star, potentially. And there you can see the spectrum going way past 10 to the 30, up to 10 to the 36 or something, much, much bigger. And so then the question is, like, every 100,000 years, is the sun going to give us one of those? I don't know.
Hopefully not.
Yeah, especially not tomorrow. No.
Have you tried other models? Do they give the same results as Wacom?
Yeah, so Charlie Jackman has been, he does a slightly different kind of modeling for these estimates, and others have looked, the groups in Scandinavia have also looked at using other models, and I think it's a pretty robust result. Wacom has the advantage of having all of the meteorology, and I forget the terminology, but you can put in all the wet chemistry. It's very sophisticated, and I would say that it's probably doing the best job of modeling these events, but I think qualitatively they're not different than the more simple models. Everyone's like making sure Han Lee is running back and forth.
Mike, I'll ask him. Oh, never mind. You can tell him. So 100 gigawatts is a lot. It's especially if it's average. If you get it over 2 weeks,
Right.
You would not see an auroral storm lasting 2 weeks. And so, as you recall, I was surprised by this number because we were trying to do something meaningful with an energy, a flux per unit area or something where you could compare something and say, well, how important is this likely to be for the mesosphere where most of these particles land?
Right.
And so they said, well, let's compare it to something some reference point that we know about, like the aurora. So, hence the suggestion of turning it into a hemispheric power. And since I've always been somewhat skeptical of this source as a significant mesospheric supply, if there's really 100 gigawatts going into the mesosphere during these stormy times, during these fairly common events, it really puts this medium energy electrons back on the map. So if this holds up, we really have to consider that as a
this year was kind of unremarkable. Really, that 100 gigawatts is driven by effectively the maximum value here and the fact that it has to go down something like a factor of 10.
It all goes somewhere.
It went somewhere.
So
now, some of these are the kind of events that Jan has simulated where the magnetopause comes and they're just gone to the solar wind.
Right, so I thought you were going to talk a little bit about the waterfall coming out of the bucket. I mean,
yeah.
right, I mean, the point.
Yeah.
You're running out of time.
Right.
But I mean,
That's
the
a whole
point was
other
that it's
analogy.
hard to measure what's going into the lost cone.
Very hard.
At 850 kilometers, where the typical NOAA DMSP satellites measure it in a quantitative way. I'm just paraphrasing what you told me a month ago, because you're looking at this fuzzy boundary where it's hard to know what's really in the lost cone and what's just reflecting back. But this way, you're looking at the global integrated quantity, and
it's got its own limitations.
So I guess there's a question there
probably more
somewhere.
robust.
How does Firebird get around this problem?
It doesn't really. The Firebird science is really going after the microphysics of the bursts, but I would say that its value is in these conjunction intervals, if I can flip back, where we can compare at a moment for conditions that we think we understand what that difference should be. We can really start testing the models to make sure that, yeah, verily, in the loss cone, it should be a factor of 100 less than the trap component when conditions are like that. You can't be everywhere all the time, which is what Firebird would have to do to be able to answer, take it to that next level. But if we can confirm over enough times and over enough range of conditions that we understand how to turn the knob when the conditions are like that, then we can really start appealing to the models more convincingly and confidently.
300 kilometers, say. Everything's in the lost code by then, right? I mean, by the time you get, well, maybe not. At these high energies, I guess you still have.
It's tough, yeah.
But I mean, you get down to an altitude where the precipitation dominates over the reflection, and so I'm just wondering, there must be an atmospheric measurement you can make.
And that's part.
Moon measurement. You can't fly at 80 kilometers.
That's what Barrel did.
Robin 200.
Right. Robin Millen did that with the balloon experiment, which is X-rays, which scatter like mad. So it's again, that's a remote sensing. You're looking at a secondary creation. You have to kind of get at it from multiple directions, and that's been.
But maybe there's some altitude at which you could say,
yeah,
this really is a flux that's entering the atmosphere. Say at 200 or something, and measure it with something simple.
Right. No. We did, but Barrel wasn't on, or Firebird didn't have data. So Murphy's Law.
And is there an explanation for the spike at the quarantine event? Because now it said that the nitrate peak cannot be explained by flares.
Right.
Is there some volcano event or?
I don't know that anyone's come forward with a hypothesis for what that is, other than it may have been something, or it could have been a penguin walking by or something.
Oh. That's right. You don't see that every year. It's just that year. There's, that's.
Yeah, it might have been.
There should be a record.
There might be, yeah.
Okay. Yeah. That signal looks clean, and it's just that year really spectacular, I think.
And geophysical data are very noisy, and we like to make correlations between two noisy data sets, and that's kind of what happened, I think, to get us to that point where we really had to get more quantitative than that.
Get people thinking. All right, thank you.
Thank you.
Oh, if any of you want to go to dinner, let me know with Harlan.
Apologize.
No, that's okay. It's not.
I'm not sure. He pressed something.
Yeah.